Hi everyone, this is ISPC and Unreal Engine 4, a peek behind the curtain. I'm Jeff Roos, Senior Developer Relations Engineer, and I'm joined by Michael Lentine, Lead Physics Programmer at Epic Games, and Martin Wilson, a Senior Animation Programmer, also at Epic Games. Here's the legal. All right, so what we're going to talk about today is, first of all, why are we here? What is ISPC? We'll go into a little bit about ISPC programming. We'll talk about Unreal's integration of ISPC, and then inside Unreal, what Chaos, the physics engine, does with ISPC, and also what animation does, and then we'll wrap up. Okay, so why are we here? So exploiting parallelism was essential for obtaining peak performance in Chaos and animation, even on a modest high-end system. What does that mean? So there's two kinds of parallelism. So there's task parallelism, which means multi-threading and multi-core. There's also SIMD parallelism, which means SIMD vector intrinsics. In this talk, we're talking about SIMD parallelism, and that's mostly what ISPC addresses. So the problem is that C++ doesn't cut it for high performance code. When you're working with an auto vectorizer in MSVC or Clang, it's difficult to get the auto vectorizer to recognize what your intentions are, and it's difficult to control. If you fall outside of what it expects, then you get no performance gain. And so we need to solve that problem. There's a couple of ways to do it. Usually there's intrinsics, but again, those are hard and platform specific and instruction set specific. If you're spending all your time writing vector intrinsics, there's no time to create your games. So with ISPC, it's meant to make it easier to get all of those floating point operations out of your CPU without being an intrinsics ninja. And how to do that is with the Intel SPMD compiler called ISPC. So it wouldn't be an Intel talk without an architecture CPU diagram. So where are we in the CPU? So if you look, the circles represent the vector units where all the execution happens. And this is an Ice Lake U, so that's a 10th gen quad-core CPU. So what is this ISPC thing? ISPC is the Intel SPMD program compiler. SPMD stands for Single Program Multiple Data. It's a compiler and a language for writing SIMD vector code. And it's based on LLVM. It's open source, and you can compile from many SIMD architectures. And it generates high-performance code for many different vector instruction sets, including SSE, AVX, AVX2, AVX512, and even ARM Neon. The problem until now has been supporting many different vector instruction sets. The abstraction is costly to maintain, and adding new functions means writing the same algorithm many times for different platforms and instruction set targets. This can take a lot of time. ISPC solves all of these problems all at once. The language looks very much like C. It's simple to use, easy to navigate, easy to integrate with existing code bases, and the function calls to get into ISPC just are C. So why would we use ISPC? Well, it's easy to speed up existing code using SIMD quickly. Intrinsics are hard, like I said, instruction set specific. If you had an existing code base that had SSE 4 wide, adding AVX would mean another permutation of that code, so another copy of it. Unreal by itself uses SSE too in a platform abstraction. And integration into Unreal benefits all games built on it. So if you are building an Unreal game, you can make use of this too. It also works everywhere that Unreal does. So there's Windows, Mac, Linux, PS4, Xbox, and ARM support already built in. It's proven technology. Other integrations have used it already, including Embry, which powers lightmass, static lighting, and also the ISPC texture compressor, which is the default for BC6H, BC7, and ASTC textures. So a little bit about what ISPC looks like. It is not an auto-vectorizing compiler. Um, it doesn't generate vector code by analyzing and transforming scalar loops like ICC, Clang, GCC, and MSVC. It's more of a what you see is what you get vectorizing compiler. The programmer tells ISPC what's vector and what's scalar. Vector types are explicit and not discovered like with a auto-vectorizing compiler. And there's a clean separation of SIMD vector and task programming models. It also works with existing C++ memory allocations and data buffers. In fact, most of the time you're passing C and C++ data directly into ISPC to work on it in a much faster way. So ISPC is, like I said before, is built on the industry standard open source LLVM. ISPC is then translated into LLVM IR, where it is fed into LLVM and turned into vector instructions. So the project is open source on GitHub, and then we also accept issues and pull requests. So what does the language look like? Like I said, it looks very much like C, so it's easy to understand and read. The code looks sequential, but executes in parallel, like a shader. And it makes it very easy to mix scalar and vector computation. There's explicit vectorization using two new ISPC language keywords, uniform and varying, and again, not a vectorizing compiler. So this is what it looks like. So here's the simple RGB to gray function. You have n iterations in a loop, and you're pulling from red, green, and blue buffers and outputting into the gray. So we'll go into this a little bit more, what it looks like in the assembly later, but this is basically what the language looks like. So very much like C, and it's basically like shader programming for the CPU. So the key concept in ISPC is the concept of uniform versus varying data. Scalar data, or uniform, are results in scalar registers, so EAX, EBX, ECX, etc. And all SIMD lanes share the same value. So when you have a uniform float, that means a single float of, with the 0 in it in this example. And what varying is it's vector data. So the results will be in a SIMD register. So when you're working with 4-wide SIMD, that means XMM. And when you're working with 8-wide, it's YMM. And 16-wide, it's ZMM. So in ISPC, varying is the default. Each SIMD lane gets its own unique value, and the width of the varying type is dependent on the instruction set you are targeting. So that's what this looks like. This would be if you had a varying float and you're working with 8-wide data. So each SIMD lane has its own number here. Now there's a couple of built-in variables to help along the way. Program count, which is a uniform int. So that is the vector width used in the compilation unit. So with SSE, like I said before, that's 4. And with AVX, that would be 8. And this is the number of 32-bit values that are packed into a vector register. Now, you can have a couple of different types, and we'll get into that a little bit later. There's int16 and int8 widths. So you could have more than 8 for AVX, for example. So this is the width of a varying variable. There's also program index, which has type varying int, and that's initialized to 0 to program count -1. So if you're working with SSE, program count, depending on which lane you're working on, is 0, 1, 2, or 3. And so this makes it really easy to index into arrays from a uniform pointer, like so. All right, so control flow has everything you'd expect from C and C++. You've got conditionals, if, else, and switch. You've got loops for while and do while. And it's got also a couple other ones for convenience and performance, including the one that you saw in the RGB to gray example earlier, which is for each active, for each tiled and for each unique. We'll go through those a little bit. And then for performance, there's cif, cwhile, cdo, and cfor to give a hint to where your control flow is most likely to go. So there are some special iteration constructs. I mentioned in the last slide that there's for each. And what that does is it iterates over the range of 0 to n in chunks of program count elements. So instead of each loop being once through, you might do eight chunks or 8 elements at the same time. So in chunks of 8. So variables will have type of varying int, and also if your data doesn't match exactly to the for each, so or the program count elements, it handles the masking correctly. So if you're doing 7 iterations through a loop, that will be handled correctly if you're running on 8 wide. So for each active is an interesting one that serially iterates over active lanes. If you're doing if statements and you're down very nested and you need to do a heavy operation using all of your SIMD lanes, for example, this is a good one to use, and we have an example of this later. For each unique is serially iterate over unique values in varying value x, and this is useful for things that repeat. So if you're doing transforms of a set of vertices or vertices, and you've got several of them next to each other, for each unique can save you some computation time by not doing that same calculation multiple times, and we've got an example of that too. Arrays work as expected. Arrays of uniforms are just like C and C++ arrays, and often it can be and often is passed directly from C and C++. So that's we have a couple of different kinds of loads here. There's a vector load, that's a single value being loaded for all lanes. You've got a vector load, remember program index, that gives you 0, 1, 2, 3. And then you have a gather. So a gather is something we'll talk a little bit more about later. And what that means is you're loading from a different place for each SIMD lane. It's not where data is packed. And a broadcast is where you're loading the same value into all of the SIMD lanes. All right, so structures look about the same as C and C++. So typically you'll have your memory representation where you have RGB, RGB, RGB repeating. So what happens if you want to work on just the R's? So that's what I said, that's what a gather is. And this is painful because potentially in the worst case, you could be loading your values from different cache lines. And this means that you could be loading 8 separate cache lines for AVX for a single load. So that could be problematic. ISPC does warn you against these gathers, but it will always vectorize, and sometimes the compiler can reason about and merge gathers into vector loads. And recent Intel processors have added dedicated gather instructions to help this case further, but it's still slower than a vector load. So what if your data looked like this, where your R's and G's and B's repeated? Then you could do an efficient vector load. So this is a more efficient layout on the bottom one. So packed vector loads are always better, and if you can transform your data to use this, it's going to give you more speed. Now there are some ways around this, and we'll talk about that a little bit later. All right, so let's come back to the RGB to gray example. We know that for this gray, we've got a couple of multiplies, you got a couple of adds, and got a couple of loads. So we've got some constants here. Here's the emitted assembly. Now, so we have some constants, the 0.3, the 0.59, and the 0.11. That's what the broadcasts are. And then you've got loads, multiplies, and then FMAs, which is multiplies and adds in one instruction, and then you've got a store. So we've got 3 loads, 3 multiplies, 2 adds, and a store. So what this is doing is, since we're using the YMM registers, you're doing 8 of these at a time. So whereas C++ might be doing 1 of these at a time, now you can get 8 times the amount of throughput that you could before. So about memory and performance, ISPC is great at generating code for you, but it can't rearrange your data. We've talked a little bit about gathers. It can't speed up memory accesses for you. So data layout is very important. Data layout is very good if it's in the cache and if it's in the right layout. Prefetch can help if you've got very large loops. ISPC can help with that. And I mentioned before that gather and scatter, which is scatter is when you're storing to memory the same way as shown before. So those can be painful instructions. So you can prefer structure of arrays layout or array of structure of arrays layout, and those will generate vector loads and stores. And Mike Acton has this great presentation about data-oriented design. Check out his talk. So some other language features of ISPC. ISPC provides a rich standard library with logical operators, bit operators, math, clamping, transcendentals, so sine, cosine, tangent, random number generators, cross lanes, reductions. Also, we don't cover them here, but we've got pointers, array of structures, helpers, C-like references, C++-like references, and then operator overloading, task systems, and then support for multiple math libraries. So why is this good? So it's good because programmers no longer need to know the instruction set that they're targeting to write good vector code. It's more accessible to programmers who aren't familiar with SIMD intrinsics, and more programmers are able to fully utilize the CPU in various areas of game development. It's also easier to read and maintain. It looks like scalar code. Again, you're not writing a different version for every platform target, so it's easier to maintain that way because there's less code. And supporting a new instruction set is as easy as changing a command line option and recompiling. When we added console support just recently, it was just that easy. And it's common to achieve big speedups on 4-wide SSE units and even bigger speedups on 8-wide AVX units without having to write a different set of intrinsics for each one. So let's go through an example now. Let's put it all together. This is the dot product that you should all be familiar with. And what this does is it calculates a dot 4 product of a bunch of vectors in a loop, and this uses the 4-wide XMM registers. So this is the common case. So each run through the loop is doing one single dot product and then storing it. So what if you needed more speed? Well, the way that you do it before is you'd use 256-bit registers, the AVX registers, and so you'd write some more intrinsics, and you'd have a guard in there for platforms that don't support AVX. So in the top loop, you have 2 dot 4s, and the bottom one is a single one to catch the cases where your number of instances doesn't match up with 2, so the odd cases. All right, great. So that's better. That's faster. So this is what the ISPC looks like for the first example. This is the same as the first example. This uses 4-wide XMM registers. You'll see the uniform loop counter means iterate exactly that many times through the loop. And this will work for all targets instead of just the x86 targets like the intrinsics will. And so here's the next improvement. So what if we wanted to do a ton of these dot 4s in parallel? Well, you can use varying. So now you're doing 4, 8, or 16.4s in parallel, one for each SIMD lane depending on which instruction set you're using. So for each handles the cases where the loop counter doesn't match up with the SIMD width, but there's still a problem. Your data probably isn't laid out in the most friendly way here, so you'll get some gathers and scatters. The data is still an array of structures and won't use vector loads and stores. So what if we could fix that too? All right, what if you could combine the best of intrinsics and varying? So the thing here is that this auto scales. So now you're doing 1, 2, or 4.4s per iteration, depending on whether you're using SSE AVX or AVX 512. And when unrolled, this can be even more effective because ISPC will coalesce the vector loads and stores. So this is very useful for certain classes of algorithms like normalization if you're doing tons of those in a loop. And this really shows the power of ISPC. This is one algorithm that can scale automatically from SSE all the way to AVX 512 and supports every platform target in the most optimal way. So this surely beats writing intrinsics. So next we'll talk a little bit about what the Unreal integration of ISPC looks like. So ISPC is available in Unreal from 4.23, and then like I said before, console support was added in 4.25. It's used in chaos physics and animation systems today, and it also supports custom usages. So if you've got a system that you've written for CPU that uses that's very heavy, you can use ISPC as well. So all you have to do to make use of ISPC is include the module in your build.cs, add ISPC files to your project, include the generated header that comes out of the build tool, and then Unreal Build Tool will handle the rest. It's really very easy. It outputs object files that are put together by the linker, just like you'd expect from C and C++. And all of this was done to be as seamless as possible for Unreal developers. So when would you use ISPC in Unreal? Well, it's very good for dense compute-bound workloads, heavy math like physics intersection testing, cloth, or CPU vertex transformations. It's best when it's used with contiguous memory, so when you load, manipulate, and store, like Unreal's T-array. It's also best when there's no data dependency between operations, and it's especially useful when combined with parallel for and batching. So that's from Unreal's integration, and now we'll talk with Michael and Teen a little bit about how it was used in chaos.
Thanks, Jeff. My name is Michael Lentin, and I run the physics team at Epic Games. Today I'm going to talk, as Jeff said, about how ISPC is used inside the chaos physics engine. Next slide. So before we get into that, let's talk a little bit about what is chaos. So the chaos physics engine is our next generation physics engine inside of UE4, which provides a number of features for both general physics and destruction-specific technology. So the list of the features is on the slide. It provides non-convex collisions. It provides a new field system, which allows you to specify a region in space and set any arbitrary physics properties, such as friction or restitution within that region. It also supports tight integration with other systems inside the engine, such as Nagra and audio. It provides an interactive caching system that allows you to author a simulation, record it at sub-real-time rates if necessary, and then play it back at substantially improved performance without actively running physics. But then it allows interactions with non-cached objects such as characters or other dynamic objects in the world to then make the objects that the cached objects interact with go dynamic, which gives a feel of a dynamic large resolution simulation without the computational cost of needing to simulate every body. It also supports a new dedicated physics thread mode. So this allows us to tick physics at a fixed rate or at rates that are different from the rest of the game thread tick. So for instance, if you have physics heavy scenes, you could tick the game thread at 60 frames per second, whereas tick the physics at 30 frames per second. Alternatively, you could, if you want high accuracy, tick the physics thread at say 120 or 240 frames per second, while you tick the rest of the game at say 30 or 60 frames per second. It also provides destruction-specific technology such as the notion of a geometry collection. So the geometry collection is a new type that's somewhere between a skeletal mesh and a static mesh. It allows a number of destructible pieces to be part of the same component, but doesn't have the overhead of linear blend skinning and other more complex features that you need for full character simulation. This allows us to achieve substantially more performance than having hundreds or thousands or tens of thousands of static mesh objects in the world, but still allow a large scale of objects in the world, more than you could get out of a skeletal mesh. For destruction specifically, we've created a number of cutting tools for breaking up objects, and we allow a LOD system that lets low-end devices break off, say, a few objects, and higher-end devices break off significantly more objects using the same artistically created setup. And finally, it introduces the notion of dynamic strain evaluation for destructible objects, such that when collisions happen or some other force happens in a specific region, it will then compute which pieces in that region should break off. So chaos uses ISPC for a few reasons. So the first is that ISPC is a nice, easy, convenient way to take advantage of SIMD. So it provides a simple shader-like interface for performance optimizations. Perhaps the most important aspect of ISPC is that it works across all platforms without needing to use any specific intrinsic code. So this means that we don't have to have like a Neon version, an SSE version, we can just have the ISPC version. ISPC is currently actively used by Chaos, both inside of Fortnite and our destruction demos. So here you can see a figure that shows a performance comparison with and without ISPC on consoles, on Xbox One and PS4. And even with a fairly limited use case at this point, within Fortnite, we still get a 10 or 15% improvement when we start using more heavy physics. Next slide. So I'm going to go through a couple different examples of where ISPC is used in chaos. So the first is the rigid skinning that I referred to before, that is part of the geometry collections. So here what we need to do is take all of the rigid body transforms for all the pieces that are moving through the world and apply that to all of the render vertices associated with the particular piece that's being moved. So we can do this using this code here, using ISPC, where we can use our SIMD lanes to process a number of vertices at the same time. Next slide. So another case of use of ISPC, specifically on the destruction side of things, is computing the bounding boxes for geometry collections. So as I mentioned, geometry collections are a combination of hundreds or thousands or tens of thousands of different independently moving pieces. And so in order to compute an overall bounding box for that destructible object, we can then break each of that set of objects into a number of different subboxes, compute those subboxes, and then reduce to create the final bounding box. Next slide. So in addition to destruction technology, we use it in a couple of other places in order to get performance benefits. The first is in the scene query system. So what we do for scene queries in chaos is we defer creation of acceleration structures if there are too many objects streaming in at once, because ultimately it'll cause hitches or delays if you just spend all that time within a single frame. So we allow the acceleration structure to be computed over a few different frames, but this means if we have a scene query against an object that was just streamed in, happen between that before that acceleration structure has finished completing, we essentially just have to assume that it passes the acceleration structure test, and we have to do some queries against it. if the number of things in this situation, so if we're streaming really, really fast, for instance, becomes too large, then this can start getting fairly performance intensive. So what we can do with ISPC here is we can process all of the elements in that array that is outside of the acceleration structure. And for each of those elements processed with ISPC, we can call directly into our C++ code that determines whether this object needs to be considered or not. Of course, there's some overhead to converting things from C++ to ISPC. It can involve things like additional function calls or memory allocations. We see certainly larger benefits as the number of objects in this parallel list gets significantly larger. If you only have the order of tens of objects kind of in an array that you're looking to process with ISPC, it may be more beneficial to avoid it. But as you start scaling up to hundreds or thousands or tens of thousands of elements in your array, then you can start seeing substantial benefits. Next slide. Another example that we see pretty big benefits using ISPC is on rigid chains. So rigid chains are often used to generate skins that we use in Fortnite. Rigid chains use fairly simple, fairly math-heavy calculations, as you can see kind of in this ISPC snippet here. So this makes it very easy to convert all of this data to uniforms so that it performs optimally and as close as possible to intrinsics. So in this case, we'd have no performance loss compared to directly using intrinsics, but while still getting, of course, the benefits of a single language without needing the platform-specific code that we mentioned earlier. And even just converting a fairly small amount of the rigid chain calculations into ISPC, we can get overall benefits on the order of 15 or 20% for a particular skin within Fortnite. So we're also continuously exploring other ways to optimize chaos using ISPC, both for Fortnite applications as well as inside engine code, so that all of our licensees can take advantage of games like this. Now I'm going to hand it over to my colleague Martin, who will talk a little bit about ISPC and the animation systems.
Thank you, Michael. I'm Martin Wilson, Senior Programmer on the animation team, and have been with Epic for 7 years. I'm going to talk briefly about how we've used ISPC on the animation team in Unreal. Unreal is a multi-platform engine. We currently support 8 platforms, but that will be going up to 10 with the upcoming next generation consoles. As Jeff touched upon, maintaining platform-specific code across so many target platforms can be a huge time sink, and the engine animation team at Epic has historically been pretty small. Because of this, vectorization is not something we've ever pursued. Instead, when it comes to performance improvements, we've focused on high-level changes and multi-threading, with vectorization support coming purely from library code in UV4, e.g. F-transform. Fortnite is obviously a major focus for us right now, and the game is actually a big driver for character performance. The Battle Royale mode is the most players we've ever had in a game we've built, and our limited time modes such as Team Rumble and 50v50 tend towards big groups of players. This limits what we can accomplish with our normal performance tricks, as it were. Approaches such as limiting update rate or animating fewer bones don't work as well when the characters are close to you and you can see those effects in action. On top of this, in the latest season we've added NPCs to the game. They also require animation, and then there's always the question of what we can do next. If we could run twice as many characters at the same frame rate, what would that allow us to do gameplay-wise that we can't do now? So as I said, performance is always critical for us. ISPC's ability to write code once and hit all target platforms is a huge win for our team, and allows us to focus resources on building animation tech and supporting game teams, rather than maintaining multiple versions of basically the same code. So how have we used ISPC so far? The main focus has been on runtime performance, basically things that affect shipping clients only, as that is our number one priority, the performance of the clients that the player is using. I'm going to talk about a couple of those here. Pose blending is the ideal scenario for something like ISPC, as the logic is already running through contiguous arrays of data. As you can see on the right, the code in ISPC is very straightforward and is very similar to the original C++ code. In testing, we saw almost 2 times the performance from ISPC over the original code. At runtime, all animation data in Unreal is stored in a compressed format to save memory, so decompressing that data is a big part of the cost of the animation system. We have multiple different compression schemes in UV4, and so each one requires an ISPC implementation. Again, one of the strengths of ISPC is that the resulting code matches fairly well to the C++ version, allowing anyone familiar with the original decompression code to be able to work in the ISPC version too. In testing, we found a performance benefit of between 1.5 and 2 times using ISPC, depending on the compression scheme used. So isolated performance tests are all well and good, but what does that actually mean for a game? Here on this graph you can see two performance captures taken directly from Fortnite, one built with ISPC, the dark blue line, and one without. Frame-to-frame performance obviously fluctuates, as can be seen, but overall we see an obvious gain from using ISPC, even with the rather straightforward changes we've made so far. So we've talked a lot about the upsides of using ISPC, but are there any downsides? Well, mostly no. There are a couple of things that have affected our implementation that could well be things other people see. Firstly, something that Jeff touched on earlier is that ISPC depends on the surrounding code and data being in a format conducive to vectorization. A lot of UV4 animation code at a low level is over a decade old at this point and will need some rewriting to work best with ISPC. Secondly, our current implementation requires that we have two code paths in UV4, an ISPC version and a non-ISPC version. Certainly that's better than N code paths hitting each target platform individually, but it's still duplication of logic that could be a source of bugs. Ideally going forwards, when we're happy everything's solid and shippable, we will just have the one ISPC code path. So far we've been looking at what is the biggest bang for buck we can get in terms of ISPC, and the changes we've done for runtime performance will be going out 4.25. But there are other things we are looking at as future work listed here. Curve blending and URO interpolation are two further runtime changes that we could see good performance benefits from using ISPC in. And animation compression is always something we want to run faster, as it can be a limiter on iteration speed for users of the editor and could also slow down build generation at cook time. And with that, I'll hand you back to Jeff. Thank you.
All right, thanks, Martin. So ISPC optimizations regularly show performance gains over C++. There's plenty more that we didn't cover here, and I invite you to go look at the ISPC project that has a user's guide and a great performance guide. So like I said before, Unreal developers can now use ISPC in their games from 4.23 onward, and we added full platform support in 4.25, so Windows, Mac, Linux, PS4, Xbox, and ARM. We welcome feedback. My Twitter handle is there. So we have some links here. If you're looking at the PDF slides, those will be links. So I invite you to go check out these links for ISPC. And yeah, enjoy ISPC. It's a great language. Thank you for your time.